What's up, everybody? Wanted to put this video together and get it out to you guys just to serve as a review of some of the things we should have seen over the past 2 weeks. We're sort of continuing on this 2 week cycle, and we're coming up on our next quiz. So, I apologize for the lack of diversity in assignments here. I tried my best to keep on with what we were doing before we all left school. I thought the best way and the easiest way was to, keep with the simulations because they're pretty simple, they're pretty straightforward, and they are, it's easy to ask just one or two, or I should say three, four, five. I know there's a little bit more with the fourth and the fifth, but there were two simulations there. So I wanted to just go back over them, talk about what you should have seen, some of the questions that we had, and I don't know what happened to all of my other tabs. So give me one moment, please. There they are. Anyway, so starting off with the first simulation. Okay, and my screen is a little wonky here. Of course, now I'm gonna have to scroll around. I don't want to. We were playing around with the spring. There we go. Okay, so as we released it and we played it, we saw that it creates this graph. We have two different types of graphs here, okay? We have a bar graph on the left-hand side here, and there's a line graph on the right-hand side. Again, you can scroll down, go full screen. I'm not doing that because it's going to mess up the screencast here. Just remember that that's an easy way to make sure that you can see everything at once, okay? But looking at some of the questions I asked you, let's say, so what are two ways we can give the energy or give energy to the spring? Easy. We can either push it in or we can pull it out, right? And that is going to require us to use a force. We are going to put a force on that spring, all right? So when we do that, when we put a force on the spring, are we transferring or transforming energy? Okay, remember, if I am transferring energy, think transferring money. I'm going to transfer money from my account to yours. It's still money, it's just in a different place. So when I transfer energy, it is the same kind of energy in a different place. And that's what we're doing here. We are taking potential energy from us and putting it into the spring. So getting into that second part of the question there, what sort of energy? Potential energy. Okay. If we let the spring go, we took a look at that. I could reset this, stretch it out, and play it again. I can see that I start with a lot of potential energy, and as I go along here, it transfers to kinetic energy, and after a while, all of it turned into heat. All of it turned into thermal energy, okay? So something else to note there, okay? And that's why it doesn't continue on forever. That heat is essentially getting into the fourth and fifth question, that heat is being transferred out into the atmosphere. Right? If you were to rub your hands together, you're taking potential energy in your body, turning it into kinetic energy to move your hands, and then heat energy is escaping through the atmosphere, throughout the air around you. Okay, so that covers that first simulation. So let's get on to the second one. Second one, a little bit simpler here, okay? How can you make forces between the charges get larger? What happens with the forces if they are the same or opposite, okay? And the big idea here is that obviously we know that opposite charges attract, like charges are going to repel, right? But we can see that that has a very different effect on the potential energy over here. And that's what we're looking at. So if I have the same charges, pushing them closer, is generally going to make that potential energy go up, whereas it's almost the opposite as the charges become opposite. Okay, so the potential energy is very high when opposite charges are away from each other, whereas the potential energy is high when like charges are close to each other. Okay, so a little bit different there. Looking at the third one, looking at the third simulation, very similar, except now we were looking at the magnitudes of the charges. So we have the same concept in that if we have, let's say, opposite charges, I move them away from each other, it gives me that high potential energy. But what happens as I change the magnitude of these charges, right? So if I have a very small charge, let's say a positive one and a negative one, the potential energy is very low. If I ramp that up and change it to, say, a -3 and a +3, that skyrockets the potential energy, right? So the higher the magnitude of my charges, the higher the potential energy. Okay, and that's sort of the basics of what we saw in the third one. Getting into the fourth and the fifth. Okay, I grouped these together. I published them all at once. Looking at the fourth one, and this is not. There we go. Okay, so on this one, I can move these around. I can change the charges like I have in the past, but now I can press play and see what happens. So now we're combining a little bit of what we've seen through all of these different simulations so far. And I see that as I start with a high amount of potential energy, I press play, all that potential energy turns into thermal energy. That is the big thing here, right? And something else that I started mixing in here is called stability, right? I can imagine, going back to the spring example, that if I were to take a spring, squeeze it in between my fingers, that's not very stable, because if I make a very small movement in my fingers, move one out of the way, that spring is going to shoot off across the room. Charges are going to be very much the same. Any system is going to want to have very low kinetic energy. Think about if you were to take a skateboard and rest it on the street, and let's say there's a street going down the hill. If you put your skateboard at the top of the hill, it's going to roll down. What kind of energy does it have at the top of the hill? Potential energy. And that's going to go away as it rolls down the hill. Objects don't naturally want to have potential energy. They want to get rid of it. It's just easier to live that way. Okay? So keep that in mind. That's what we should have seen in the fourth simulation. Getting into the fifth one, we're getting back to our Van de Graaff. I know we have been away from this for a while. It's been a long stretch. But we should have been getting to a point where we're actually looking at the flow of electrons and what's happening at the atomic level, and why the Van de Graaff behaved the way that it did. Even getting back to explaining why the pie pans flew off when we turned it on. So I can add negative charges. You can't add any more than 5. I can see I start with very little, I start with no potential energy, and as I add electrons, not only do they spread out evenly around the Van de Graaff, but they remove the potential energy. Okay, and I can move this wand around. I can see as I pull it away, that potential energy goes even higher. And as I move it closer, right, I can see that my electrons are just itching to get out, making my potential energy even lower. And as soon as I start pulling them away, it just jumps straight down. right? Again, because it wants to have as little potential energy as possible. So if it can get rid of those electrons, they can go. If this wand was our finger, those electrons would go through our body, right? Just like the Van de Graaff shocked me plenty of times. Um, you know, the goal is to get away from having any stored energy, that potential energy. So, looking back, looking back on investigation 2 here, a couple things. Activity 1, 2, and even into 3 here, we're talking about the higher the forces, the more energy that's going to be associated with them. Obviously, we have different relationships between like charges and opposite charges. Okay. And then getting into the fourth and the fifth one here, we're looking at how specifically what happens when potential energy is released, why is it released, um, and how that relates to charges, both positive and alike. So hopefully this helps. I'm going to be publishing the quiz first thing tomorrow morning. I'm not getting a ton of questions, so I'm assuming that means we're doing all right on these. So again, let me know if you need anything. Hopefully everyone is doing well, and hopefully we'll talk soon. See ya.